Okay, thanks a lot, Peter. And first of all, I would like to thank the organizers and the organizing committee for setting up this virtual conference. And it's really great that we have this type of events and way of gathering despite the difficult circumstances worldwide. So it's a great pleasure to be here. And I'll try, I know that the audience is pretty diverse. So we all do dynamics, but very different type and application, more pure. I'm on the more pure end of the spectrum. So I'll try to give a quite gentle introductory talk, surveying my research area and especially slow chaos. You will get to know what slow chaos, what I call slow chaos very soon. And let me just point out, since Peter read out the citation of the Brin Prize, of which I'm very honored, on the pictures that you see here are a locally Hamiltonian flow to the right and a wind tree model to the left. So you will get to hear of some of the results mentioned by Peter very soon. Okay, so what is slow chaos? So first of all, to start, whatever I will be talking about today are deterministic dynamical systems. So I will not consider systems which have randomness or external noise. And mostly we will deal with flows. So you can think of them as solutions of differential equations. So everything is deterministic, but we all know very well that deterministic systems exhibit chaotic features and different degrees of chaotic features. We'll discuss them later. And we also all know the typical example, which is very much popularized to the general public, that deterministic chaos is often created. One of the distinctive features is the butterfly effect or sensitive dependence on initial conditions. So in a deterministic system with sensitive dependence, small changes of initial conditions create a very different evolution. So two nearby trajectories may diverge macroscopically. So what I call more colloquially slow chaos in contraposition to fast chaos. There is again a typo, quickly. So you want to know essentially how fast the butterfly effect happens in a system which displays it. And these names, fast chaos and slow chaos, are shortcuts for systems where the butterfly effect or the divergence of nearby trajectory is fast. And by fast, I mean exponential. So in fast chaotic systems, you have exponential, you can see exponentially diverging trajectories. And what I call slow chaos is when this divergence or this butterfly effect is slow, and slow means sub-exponential. For example, polynomial or even subpolynomial. So better term, maybe we can call hyperbolic dynamical systems are fast chaotic. And what I will tell you today about are parabolic dynamical systems. Again, hyperbolic dynamical systems, as we know, are very well understood, and there is a lot. The theory starts from the 70s. There are many names, and partially hyperbolic and non-uniformly hyperbolic. There is a lot of theory going on. And on the other hand, parabolic dynamical systems, or slowly chaotic, are much less understood. And there is no general theory. We mostly try to understand examples. And so what is the goal of my research and what I want to present you today is somehow trying to understand typical properties and typical mechanisms for chaos in parabolic systems. And again, there are motivation and application from mathematical physics and also number theory. Maybe we'll see one at the end, and yeah, probability aspects. Okay, so I want to start with a very easy example of a deterministic system to make the difference between slow and fast chaos. Many of you have probably seen mathematical billiards. So mathematical billiards, this is a real billiard that you can have in the pub. We don't have a virtual billiard to play tonight, but idealized billiard, mathematical is when you have a table, which is a planar domain, a ball, which is at a point with no mass, and the motion, as in the real billiard, happens by moving along straight lines until you hit the boundary of your table, the boundary of your domain. And I'm assuming it's smooth. And if I don't hit a corner, then I just reflect according to the law of optics. So the angle where you hit is equal to the angle after the hitting. And in a dynamical system, we are interested in, first of all, trajectories which don't hit the corners, so don't go into the pockets, and therefore keep going forever. And the billiards can have different shapes, and it's more interesting when you put, of course, obstacles or barriers in even a rectangular billiard. And you can also consider polygonal billiards, or in general, any piecewise smooth type of domain in the plane. And also infinite planar tables that we will meet in a second. So let me show you the butterfly effect in two examples of billiards. So here I'm comparing a circular scatterer with a rectangular scatterer. So the domain of the billiard is a square, but I have an obstacle in the middle. So the gray area is a scatterer or obstacle. So the circular scatterer, it's known as a Sinai billiard. It's a very famous example of hyperbolic dynamics. So if you if you take a array of parallel trajectories and look at how they hit, what happens after they hit the circular scatterer, you will see the so-called defocusing mechanism. So array of trajectories which were parallel after hitting spreads or opens up. And this defocusing mechanism is a key ingredient in the study of so-called hyperbolic billiards, of which the Sinai billiard is a key example. And this gives rise to fast chaos. So Sinai also got the Nobel Prize for studying chaotic properties of this billiard. And on the other hand, I want to compare it with a rectangular scatterer, so flat straight lines boundary. And this is a key block of the so-called Ehrenfest billiard. So here, there is also a way to see, so the butterfly effect, why nearby trajectories, for example, which are parallel, but only differ in initial position, may take a different time evolution. So, but here, if I only hit the flat part of the boundary, trajectories which were close stay close. So here there is no butterfly effect. So the only divergence of nearby trajectories is created by corners. So if I have trajectories which miss the corner versus some that hit it, then you do see that they start flowing differently in the future. So this mechanism introduces chaotic features, but it's much slower in creating the butterfly effect. So this type of billiards belong to the parabolic paradigm and to slow chaos. And more generally, if we stay in the world of billiards, we'll leave it soon, but I want to say the boundary of the planar domain determines a lot of the type of dynamics that you want to, that you need to use to understand billiards. So convex boundaries give rise to elliptic dynamical systems. And those are strictly connected to Hamiltonian dynamics, KAM theory, and it's a very interesting word, but maybe related to variational methods. On the opposite end, we have concave boundaries. Like in the case of the Sinai billiard, you can also think of this as a concave boundary because you see it from the inside of the billiard. So the convex scatterer produces a concave part on the boundary. And these are hyperbolic dynamical systems, fast chaos, as we just discussed. And in between, there are polygonal billiards. And especially actually those which we understand, the only ones which we understand well are those which have rational angles, so angles which are rational multiples of pi. And these are have been studied, and there is a beautiful mathematics related to Teichmueller dynamics, and many Fields medalists like Konsiewicz, McMullen, Yokos, Avila, Maria Mirzakhani have worked on billiards in rational polygons. So we understand them pretty well. Okay, so I want to now discuss for a second which type of chaotic properties I want to discuss. And Of course, when I say chaotic properties, there is a range of features we may be interested in, and they span from topological dynamics, so basic notions like are there periodic trajectories, are there dense trajectories, so minimality when all trajectories are dense. Then we can have ergodic theory notions, so we can study if there is an invariant measure, we can study equidistribution of trajectories and ergodicity. So we can ask if the system is ergodic. So if there are no trapping regions, no non-trivial invariant sets from the measure theoretical point of view. And going beyond in the scale, in the case of when there is an invariant measure, we can investigate mixing. So I will focus a lot on mixing. So I will remind you in a second mixing. And finally, towards the end, I will discuss spectral notions. So we will go through the whole range of chaotic features from ergodic theory to spectral theory of dynamical systems. Okay, so let me remind you what's the definition of mixing. So in a mixing flow, for example, this is a picture of a billiard in the diamond by Carl Detman. It's a simulation by Carl Detman. The billiard in the diamond is mixing. So if I flow a set, an initial set A, you see that as T grows, it equidistributes. And yeah, the definition is that if I flow a set, the proportion of A inside the given target set B will tend to the measure of B. And mixing is an important property that I will focus on, but there is a lot of variations on the mixing property, weak mixing, multiple mixing, mixing of all orders. I don't want to enter into that, but I might mention later. And again, we'll come back to the end that spectral notions, yeah, let me skip it now. So let me give you some example of motivation for why one is interested in billiards, for example, and again, the difference between fast and slow chaos. So I want to move now to two infinite billiards. So these are two famous billiards in statistical physics. And one is called the periodic Lorentz gas. Many of you may have heard of it. This is an infinite billiard where the table is the full plane to which we remove some periodic array of circular scatterers. So it's like an infinite version of the Sinai billiard, and periodic in this case. We have these circular scatterers placed periodically at the points of a lattice. And this is a very well-studied example in statistical mechanics and mathematics. There are plenty of results. I won't mention all the people who have worked onto this. And I want to compare the periodic Lorentz gas to the Ehrenfest model, also called wind tree model. So this was a variation of the periodic Lorentz gas. And it was introduced by Paul and Tatiana Ehrenfest at the beginning of the 19th century. So you see a few years after the Lorentz model. And they thought that if you maybe replace the circular scatterers in the Lorentz gas with the rectangular scatterers, maybe we will get a better, easier model to understand. So this is like the periodic Lorentz gas. It's a periodic array, but this time the scatterers are rectangles. And well, maybe surprisingly, for essentially 100 years, there were essentially no mathematical rigorous results on the Ehrenfest model. And there are several results in the past few years, and they deeply exploit Teichmueller dynamics. I mentioned here some of the people who have worked on the model. And somehow part of the difficulty is indeed that this is a slowly chaotic system, and it took us much longer to develop good tools, and we still understand only some classes of slowly chaotic systems. And just to mention one of my own contributions on the Ehrenfest model, together with Krzysztof Frączek, we proved, we studied ergodicity in the Ehrenfest model. And maybe surprisingly for people who were trying to prove ergodicity, we proved actually a negative result. So while if you look at compact, like a rectangle in a square, typically you will see ergodicity. In the Ehrenfest model, if I shoot in almost every direction, you get a billiard which is non-ergodic in a very drastic sense, in the sense that, for example, there are uncountably many ergodic components, for if you know the ergodic component, the composition. Okay. So, so this is an example of fast versus slow chaos for infinite billiards. And I want to move to, and also a motivation to the study of, well, first of all, a motivation to the study of billiards, which appear in many mathematical physics setups, but also a motivation to parabolic billiards in the case of the Ehrenfest model. And let me give you a second motivation or a second example of how parabolic flows arise in physics. And this is, I will not enter into details, but there is a famous model due to Novikov in solid state physics. And it's a model for the motion of an electron in a metal. So you assume to have a metal in a magnetic field. And the motion happens on so-called Fermi energy level surfaces. And if you use the semi-classical approximation, then the model turns out to be described by a flow on a surface. So this is the setup I want to enter now. So you have a surface of a certain genus, and a flow. So you can say that locally you have solutions of some differential equations on describing the motion of the electron. And the type of flows are actually smooth area preserving flows. So the flow that you obtain preserves area, and this area is given by a smooth two form on the surface. So you are in the setup of ergodic theory where you have an invariant measure, and this invariant measure is actually smooth. So you have a smooth flow, you are in the smooth dynamics world, and in the area preserving, volume preserving world. And equivalently, another way to describe these flows, they are locally Hamiltonian flows. So locally, they are given by solution of Hamiltonian equations. Again, I don't want to, feel free to ask me later if you want more details. But so again, the Novikov model, so motion of electrons in a metal, can be described by a surface flow. And it's a flow which describes motion on a surface, and it's smooth and preserves area. And a famous question by Vladimir Arnold from the 90s was whether these Novikov flows, these flows on surfaces arising from this model, are mixing. And for example, this is a topic on which I've worked a lot. It was also mentioned in the citation read by Peter at the beginning. And now we understand quite well what are the typical mixing properties of these flows on higher genus surfaces. And I might say something more at the end. But somehow the answer, whether they are mixing or not, depends crucially on the type of fixed points, the type of singularities of the flow. Okay, so we had two motivations, the Ehrenfest model, the Novikov model. They're both parabolic flows. And there are many more examples of parabolic flows, which are maybe not from physics, but of just generic mathematical, natural mathematical examples. So let me mention a few more parabolic flows. And if you don't know, I don't want to define them. I just want to mention for those of you who may have heard about, for example, hyperbolic geometry. If you have a hyperbolic surface, you know that the hyperbolic metric has a geodesic flow where you move along geodesics, and a companion to the hyperbolic flow, to the geodesic flow. So the geodesic flow is a fast chaotic hyperbolic, one of the basic examples of hyperbolic dynamical systems. And a companion flow to the geodesic flow is the horocycle flow. And what is plotted here are horocycle trajectories on the upper half plane. You move on a circle tangent to the real axis. And the horocycle flow is one of the most fundamental examples in dynamics of a slowly chaotic or parabolic flow. And this is very well studied, and it's been studied since the 70s, and it's one of the examples we know the best. Then this is my favorite example. I just mentioned smooth area preserving flows on surfaces. So you have a surface and a smooth flow which preserves area. These are trajectories and some fixed points that you're forced to have in higher genus. And a last class of examples come from nil manifolds or nil flows. So basic example is the Heisenberg group. You take the Heisenberg, you take a nilpotent Lie group. Again, if you don't know anything that I'm talking about, forget about it. I will skip, I will just move on soon. It just, so if you have a nilpotent Lie group and you take the quotient by a lattice, you get a nil manifold, and then you can look at one parameter flows given by left multiplication. These are called nil flows. So these are all examples of parabolic flows. So we may try to look for which type of chaotic properties do they display. And turns out that they are very different. So for example, the horocycle flow is always mixing. Nil flows are never mixing. They are not even weak mixing. There is a quite obvious reason for which they are not. And in between, we have this area preserving flows, and as I just told you, we now understand their properties, but they can be mixing or not mixing. It depends on the singularity type. So you may be a little bit disheartened because you say, okay, if I want to understand what are chaotic properties of parabolic flows, you see the behavior is very different. And in part, it's also because these flows are actually models of different type of parabolic systems. So as in hyperbolic dynamics, we can talk about uniformly hyperbolic, non-uniformly hyperbolic, or partially hyperbolic. I claim that these two classes, the horocycle flow is somehow uniformly parabolic. I don't define what it means, but smooth area preserving flows are non-uniformly parabolic and nil flows are partially parabolic. So this is one way to make sense, but nevertheless, you could say, well, maybe parabolic dynamics is just a zoo. So there's no hope to have a general theory because there are too many different type of examples. But I want to convince you that actually you can still try to identify some common features. And my research in the past few years has been oriented by this program. So try to understand parabolic dynamics by, first of all, you want to produce new examples of parabolic dynamical systems. And we don't know a lot of examples. So one thing is to perturb the known examples and produce new parabolic flows. And one easy way to do that is to study time reparameterizations. So you take a flow, move on the same trajectories, but with different speed. And it turns out that just this little change, changing the speed on which you move, produces new examples, and it can change the chaotic features. And sometimes by reparameterizing, you actually see some property appearing. For example, mixing, you may not have it in nil flows. By time changing them, you can see mixing appearing. So, okay, so we want to study more examples, produce more examples of parabolic flows, and we also want to find if there are some typical mechanisms that explain the chaotic properties of these flows. And I want to now give you an example of such a slow chaos mechanism. And this is given by shearing. Okay, so let me go back then to the butterfly effect. So we just said in a parabolic flow, the butterfly effect is slow. And I claim that in many of these systems, it also happens in a very special way. So let me show you how the butterfly effect happens through shearing. So I can start from two nearby points and flow them. And what you see in the examples I mentioned before is that the trajectories travel of these 2 points are parallel. So you kind of travel on nearby trajectories, which stay parallel, but you travel at different speed. So the blue point in my picture is faster than the red point. So if this happens, if I look at the transverse direction, if I look at an arc which connects the blue and the red point, you see that because the blue point is faster, the transverse arc shears. So basically bends in the, and yeah, shears like in the picture. So a short curve transverse to the flow gets sheared in the direction of the flow. And in many of these examples, like I will show you in a second, you get the transverse curves when sheared become almost flow trajectories. They become longer and longer and parallel to the direction of the flow. So this mechanism of shearing appears in many parabolic flows, and it's really crucial. In my mind, it's one of the key mechanisms to understand many parabolic systems. So let me show you shearing in these examples. I have 2 examples, and this one is the locally Hamiltonian flow, the Novikov flow. So I have a surface and a smooth flow which preserves area. How do you see shearing? Well, what happens, these flows are, as I said, locally Hamiltonian. So shearing happens when you see a saddle and the so-called saddle loop. So this is the picture here in red. I have a fixed point, which is a saddle. And nearby, I have a separatrix of the saddle, which forms a saddle loop. So it comes back to the same saddle, a half figure 8. And inside the saddle loop, there is an island. So there is a center, and there are closed trajectories, which are periodic. And this picture is stable under perturbation. I haven't defined the topology and the measure that I consider on this type of flows, but I claim that it's an open, seeing these saddle loops is an open property. And this saddle is a Hamiltonian saddle. So if you write down the Hamiltonian saddle, what you see is that if a point passes very close to the saddle, it slows down a lot. So if I have a set or an arc which is transverse to the flow and I flow it, the left end point of my set spends a lot of time to get out of the saddle. So it slows down a lot. And the right end point moves faster because it's farther from the saddle. So this creates shearing. So Hamiltonian saddles create shearing locally. And if I have a trap, this shearing is global. So what you see is that the set will stretch, shear and stretch, and become long and shadow a trajectory of the flow. So yeah, and not only that, so if you flow, then if a set shadows a trajectory, it will tend to equidistribute if the flow has dense trajectories and equidistributed trajectories. So, okay, I'm hiding, as I said, the trap is essential because it creates an asymmetry. So if I didn't have the trap, I would actually shear back when I go on the other side of the saddle. But the trap breaks the symmetry and produces global shearing. Okay, let me forget about this. So shearing in locally Hamiltonian flows happens like this. And the second example I wanted to mention is the horocycle flow. I will be brief here because some of you probably don't know what this flow is. But in the horocycle flow, you can also verify, actually algebraically, you can verify shearing. So if you have a geodesic, which is transverse to your horocycle, a piece of geodesic, and you push it through the horocycle flow, you will see that the geodesic shears in the direction of the horocycle. And again, if you know these flows, there is a commutation relation between geodesic and horocycle, which is responsible for this shearing. And okay, the key message is that also in the horocycle flow, you see shearing. And this was a key phenomenon exploited, for example, by Marcus in the 70s to prove actually mixing of all orders or some of the properties of horocycle flows. Okay, so why do we care about shearing? So shearing is key in explaining some of the chaotic features. And here I want to show you what is a mechanism for chaos, for mixing in parabolic flows. I call it mixing via shearing. So let me recall you. If I have a ergodic system, it means that the typical trajectories are equidistributed. So imagine that I have a flow which is ergodic. So the typical trajectory of my flow equidistributes. And I want to know if it's mixing. So if when I flow a set, the image of the set equidistribute. And here's the recipe for mixing. If you have ergodicity and shearing, you can prove mixing. So this is a quick recipe. You need unique ergodicity and unique shearing in the direction of the flow, to be more precise. But this is a recipe for mixing. So let me show you this recipe, how it works for flows on surfaces with a trap. So again, I take a set and I can maybe cover this set by transverse curves, by Fubini. And each of these transverse curves, when I flow it, shears. And if it shears in the direction of the flow, it will shadow a trajectory of the flow. So as it shears, it becomes longer and longer, and it shadows a flow trajectory. So if the flow is ergodic, this trajectory will equidistribute. So what do I get? That each piece of A, when I flow it, will become equidistributed. So again, ergodicity is an equidistribution of trajectories. Mixing is equidistribution of sets. But if I have shearing, pieces of my set shear and become like long trajectories, so equidistribute. So this is a way to deduce mixing from ergodicity. And it's really a key mechanism which was used to prove mixing for the horocycle flow, for smooth area preserving flows, and also for time changes of the flows. So it's a really ubiquitous type of mechanism in parabolic dynamics, in my opinion, very crucial. Well, not only mine. Okay, so now what I want to move on to is, great, we have this great geometric mechanism, shearing, and we used it to prove mixing in many, many setups of parabolic dynamics. Can we do something more with it? Can we prove stronger, further chaotic properties using shearing? And for example, with Giovanni Forni, we proved actually a case of a conjecture by Katok and Duvenot on time changes of the horocycle flow. We proved we understood that the nature of the spectrum using mixing. But I want to mention a very, very celebrated example where shearing played a crucial role. And this is in the work of Marina Ratner. So I don't know, some of you, if you know of homogeneous dynamics, probably you heard of her. Marina Ratner died just a few years ago. And she studied a lot the horocycle flow, and more in general, unipotent flows. And in the context of homogeneous dynamics, so quotient of Lie groups, unipotent flows. And she proved some beautiful theorems known as Ratner's theorems, and they are a set of rigidity results, which I will not describe. This is an ICM talk, which I found out happened in Zurich, where I'm based now, by Marina Ratner. And these celebrated theorems actually have found a lot of applications in number theory, first of all, and also in billiards, in actually the Lorentz gas by the work of Strombergson and Markloff, and also in probability theory and in physics. And also they were inspiration for the work of Eskin and Mirzakhani, which gave Mariam the Fields Medal and Eskin the Breakthrough Prize. So they're very important. And a key property in her work is a shearing property. So it's a shearing property that we nowadays call the Ratner property. So the Ratner property is, in some sense, a quantitative version of parabolic shearing. So I cannot give the formal definition here, but I can give you the spirit of the Marina Ratner's property. So the picture that she wants to see that for most points, for most pair of points, you see shearing. And if the 2 points shear, you can wait until you see that they have sheared by 1. So until there is a displacement by a fixed amount, say 1. So if your flow has the Ratner property, after you see a shear by a definite amount, 1, you can realign the points. So you forget about the original red point, which is lag behind, and consider the blue point and after time t, and the red point after time t plus 1. And now you start again flowing them, and they will shear again. But if you have the Ratner property, you want to say that you are still epsilon close, so you still stay close for a time which is a constant proportion of the time it took you to see shear by 1. So it takes you some time to see shear by 1, then you realign, and for a constant proportion, for a fixed proportion of the time it took, I'm still epsilon closed. So hidden in this definition, which is actually epsilon and delta becomes quite subtle, and we'll not go into that, but in her crucial property, the Ratner property, you need to have parabolic shearing. You need to have slow shearing. So this property is only possible if shearing is slow. If you see exponential shearing, exponentials don't have this property. When I start flowing exponentially, I cannot stay epsilon close for a fixed proportion of time. So hidden, there are the fact that level sets of polynomial functions, the measure of a level set of a polynomial function. Okay, let me not go into that. But it's a key property, and it was used by Ratner to enhance given properties. So for example, if you have mixing and the Ratner property, you can upgrade your mixing to mixing of all orders or multiple mixing. It's like decay of multi-correlations. And if you have ergodicity and the Ratner property, ergodicity usually gives you control of almost every trajectory, but with the Ratner property, you can control every trajectory. And this is key in the measure rigidity type of results that she proved. Okay, so I want to go to the recent results. So there has been a lingering desire in the mathematical community to try to verify the Ratner property outside homogeneous flows and outside for other flows than horocycle flow. And a natural candidate are these smooth area preserving flows, where which have parabolic divergence, we have parabolic shearing. So ideally, so for example, Lemanchik and Touvenot, who have been asking, can we prove the Ratner property of shearing, quantitative shearing, for these flows which display shearing? Unfortunately, the problem with these flows is that they have singularities. So when you have singularities, so what happens that you can, when you have two trajectories and they are separated by a singularity, so like in my picture, one goes to the right, one to the left of a separatrix, this creates very difficult behavior to control. So this singularity gives you a very fast way of diverging that it's hard to control, that we cannot control in a parabolic fashion. So for many years, it was not clear how to overcome this difficulty. But recently, Fayyad and Kanigovsky introduced a variation of the Ratner property that is called switchable Ratner. So essentially, if you are unlucky and you have two trajectories that in the future are split up by a saddle, you get a second chance and you can try to flow backward. So if the future of your trajectories is bad, maybe you can try to flow backward, and maybe you will see the nice slow quantitative shearing a la Ratner. So if you see Ratner shearing either forward or backward in time, then you say that your flow has the switchable Ratner property. And this property is enough for all the good consequences of the original Ratner property. Okay, so I want to mention some recent results that we had on understanding smooth area preserving or locally Hamiltonian flows. So together with Adam Kanigowski and Joanna Kuaga, we could prove that these flows with traps, these Novikov flows with traps or locally Hamiltonian flows with these traps, enjoy the Ratner, switchable Ratner property. So we have singularities, but with this variation of the Ratner property, we can still prove a form of Ratner property. And so Fayyad and Kanigowski did it for genus 1. That's why they introduced their property. And we could do it for any genus. And as a corollary, for example, we can get not only mixing, but what is called the mixing of all orders. So instead of considering 2 sets, you can consider n sets and prove equidistribution for these n sets. And 2 more properties, recent results. Okay, this one maybe I don't want to go into too much. So we also studied so-called disjointness properties. So we studied the flow and the linear time scale or the linear scaling, and we proved the property called a property defined by Fuss. Sorry, I think you lost me. Can you hear me again?
Yes,
did you hear me?
Yeah. Yeah, carry on.
Good. Okay, so I mentioned there are applications to number theory, and this problem of disjointness is connected to the Sarnak conjecture on Möbius orthogonality. It's a conjecture that people are working actively in number theory, but okay. And let me skip disjointness criteria based on shearing. And finally, I want to mention spectral results. So as I said, the last step in understanding ergodic or chaotic properties are spectral properties. So we can study the Koopman operator. So I have an L2 function and I compose it with the flow and I get the Koopman operator. So spectral theory concerns the nature of the spectrum of the Koopman operator. And shearing is key also in understanding spectral properties. I briefly mentioned this, the horocycle and its time changes and Katok-Touvenot conjecture. And for this locally smooth flows on surfaces, recently Fayyad, Forni, and Kanigowski showed that if I have a flow on a torus, a linear flow on the torus, and I add a stopping point, so a point where trajectories stop and slow down when they approach it, then this very simple and very deterministic system has a countable Lebesgue spectrum. So this is a very chaotic neat type of spectrum. So somehow surprising that in such a deterministic system, you can see countable Lebesgue spectrum. And what happens if the surface has not genus 1, but higher genus? So with John Chaika, Krzysztof Frączek, and Adam Kanigowski, we recently proved that in genus 2, if you have just simple saddles, you see a very different phenomenon. So you can prove that the spectrum is the opposite. It's purely singular. So again, don't worry if you don't know the definitions, but I'm very excited now of trying to understand, to complete this picture and to understand what happens in higher genus. And it looks like there might be a dichotomy between, depending again on the type of singularities on the spectrum. So, okay, so do I have a few minutes left? How much am I doing, Peter? Sorry?
A couple of minutes, maybe.
Okay, yes, I just wanted to mention briefly in the last 2 slides some of the tools that go into all this type of results. So one tool actually to study this type of locally Hamiltonian flows, we use so-called special flow presentation. So, okay, many people do nonlinear dynamic. I'm not sure that counts as nonlinear, but okay. So at the base, there is the study of interval exchange maps, which are piecewise isometries of the interval, where you take an interval, break it up into pieces, and permute them. And these are, well, linear maps in some sense. And turns out, then you take, if you can represent this locally Hamiltonian flow as a special flows. So you take an interval exchange, and then you take a function which explodes at the discontinuities of your interval exchange. And the typical flow, for the typical flow, you need to take a function with logarithmic singularity, so it explodes like a logarithm. And there is so-called special flow representation. So you can represent your flow as the vertical flow in this picture, the vertical flow under this function, with identification from the top and the bottom given by the interval exchange. And then you want to study Birkhoff sums. So you want to study iterates of the function f composed with the interval exchange. And the function is non-integrable. So the derivative of the function is non-integrable, sorry, f prime. And understanding these Birkhoff sums is crucial to understand shearing and quantitative shearing. And this is one aspect, the very basic aspect. And then another crucial tool comes from Teichmueller dynamics and renormalization. So it turns out that it's useful to look not at one flow, but at the space of flows on surfaces. And I'm a little bit cheating, but see your original flow as a point in this larger space and look at deformations of your system. And we use to deform what's known as Teichmueller flow. And these deformations act as a zooming machine, or they give you a tool for renormalization. And the orbits of this deformation flow are called Teichmueller geodesics. And why do we do that? Because the renormalization is a fast chaotic system. And there is this interplay between your slow chaotic system and the fast chaotic system, the renormalization, which we understand better than the flow, which is renormalized. Okay, let me skip this. If anybody's interested, a crucial tool, a crucial need is to have Diophantine conditions on these flows, which in genus 1, maybe some people know, for genus 1, for tori, we have standard Diophantine condition through continued fractions. In higher genus, we need a generalization of these Diophantine conditions given through the Teichmueller geodesic flow and a cocycle, a matrix product associated to it. Okay, so the fast chaotic properties of the geodesic flow are useful to prove full measure of these Diophantine conditions. And again, if you're interested, I'm happy later in the question or maybe later privately to tell you more. Just to a final slide to summarize. I hope by now you learned what I call slowly chaotic systems or parabolic systems display a slow form of the butterfly effect. The butterfly effect happens on polynomial or subpolynomial scales. Some examples from physics are the Ehrenfest or wind tree model and the Novikov flows on surfaces. And as I said, there is a lot of work to be done in understanding typical properties of classes of parabolic systems. We saw the example of Novikov flows or smooth area preserving flows on surfaces that we start to understand well from mixing and spectral point of view. And there is hope to describe some crucial mechanisms like shearing, which play a key role in understanding parabolic flows. And if you want to learn more about mixing in smooth area preserving flows and shearing, the role of shearing, and the technical tools, I actually gave course at EHS last year or 2 years ago, which is recorded on YouTube. So YouTube is helpful and you can watch it on the EHS YouTube channel. And, yeah. You need to spend 8 hours, so this is a lot. Maybe you can look at other summaries. Okay, so I would like to stop here and thank you a lot for your attention and open the time for questions. Thank you.
Thank you very much for an excellent talk. We do have one question that has come in. Domenico Lipolis has said, we taught that there is no chaos in 2D in continuous time. Are you defining chaos as ergodicity plus mixing property, even if the Lyapunov exponents are non-positive?
Yeah, so it's all a question, what do you define? So chaos is not a well-defined notion. So as you say, you're right. Some people want positive Lyapunov exponents or want positive topological entropy. So as you said, actually all of these examples, especially flows, surfaces, are have entropy 0. So they are 0 entropy. So maybe some people will not call them chaotic. So it's a question of what you define as chaos. So they display, indeed they display butterfly, they have sensitive dependence on initial conditions. And as you say, they have mixing. So yes, it is a question of what we call chaotic. But I would say that mixing is a chaotic property. And yeah, I call all of these chaotic features. But they have 0 entropy. And actually something which people are doing nowadays, they are trying to develop better notions of entropy, so-called slow entropy. So even though the unusual entropy is 0, these systems have positive slow entropy. And you can measure slow entropy in terms of this slow divergence. And Katok has started this, Kanigovsky and other co-authors have been working. So they have positive slow entropy, okay?
Okay, so maybe we have time for one more question briefly that Rainer Klages has asked.
Weak chaos.
It appears to me that slow chaos is synonymous to what Zaslavsky and others have called weak chaos, i.e. strengthening by trajectories at less than exponential, or is there any difference?
So I'm not familiar with what exactly they define as slow chaos, but I suspect yes. So I cannot tell you on the spot what their definition is, but yes, it is a slow chaos, weak chaos, whatever you want to call it, is related to spreading of nearby orbits, which is sub-exponential. And again, I was mentioning the definition of slow entropy that was made rigorously by several authors, and there's a lot of research on proving what is the slow entropy of some of these examples. And yes, you can quantify also through slow entropy how slowly chaotic one of these systems is. So it's very much open, and there's only the beginning, I think, of yeah. So I'd be happy to look into this if you, Rainer. So if you can send me maybe the reference to Zaslavsky paper and others, I would be happy to learn more and compare it. But yeah, as I said, I was using this term quite loosely, and the results I told you are all about some specific properties like mixing. Actually, mixing is also slow, so it's not exponential, but it's polynomial or subpolynomial.